Okay, to finish out this chapter, we're going to talk about a chi-square test for association or independence. So this looks just like the chi-square test for homogeneity, except for this time we haven't taken two different random samples. We've taken one random sample, and then we've measured two different variables. And so for this one, we're sampling from a single population, which when you really think about it, seems easier. Just sampling from a single population and then measuring two variables. And so you have to be careful about what you're going to do and the way you sample things. So we've got two different write-ups depending on what you're really looking for. Are you looking for an association or are you looking for independence? So we want to perform a chi-square test of association at whatever significance level we want. So our null hypothesis would mean that there's no association, there's no relationship between them. An alternative hypothesis would be there is an association, there is a relationship between them. And then we go through and we check our conditions, random, large sample, independent. This is the exact same as what we were doing before. Our chi-squared is the same, our p-value is the same, everything's exactly the same except for the way we sampled it. Now please remember one big thing, association does not mean causation. So if you're doing an association test with a simple random sample, then what's going to happen is that you're not going to have causation. But if you do an association test with a randomized experiment, then you're going to have causation because you've done the proper experimental, the randomized experiment. So just be careful of that. Just because you're doing an association test does not mean that there is an actual causation. It just means there's a relationship there. Now, the independence test. So independence means that they do not affect each other. Dependence means they do affect each other. So this kind of flip-flops from the association because there is no association should be our null. There's no relationship. So independence would be our null because they don't affect each other. And so when we start talking about the independence test, we are saying first that they are independent because there is no effect between the two, or they are not independent means they do affect them. The same thing, just different wording. And it throws people off because on association, we put no association in association. This one we do independent, not independent. So the no are not flip-flops, but the idea behind association and independence, the idea behind it stays the same. So our null is there is no relationship, there's no effect to probability, and then our alternative should be there is a relationship, there is an effect of probability. Everything else is exactly the same. It's the way we worded at the top and the way we sampled our data. So let's work through one. In an example from chapter 5, we investigated the relationship between gender and having allergies for a random sample of 40 students who completed a census at school survey. Here's a two-way table that summarizes the data. Do the data provide convincing evidence of an association between gender and having allergies for U.S. high school students who filled out the survey? So we want to perform a chi-square test for association. Oops, sorry about that. I thought I was back on pen mode. At a 0.05 significance level. Our null is there is no association, and our alternative is there is an association. So we're going to check our conditions. We had a simple random sample of 40 students. And then we're going to check those expected values. So for our expected values, we're going to go to our explanatory variable. So we're assuming gender's explanatory variable. So we're going to look here. And 18 out of 40 and 22 out of 40 will give us the proportions we need to help find those values. So 18 out of 40 is 0.45. And 22 out of 40 is 0.55. Now to calculate how many we'd expect to have allergies of females, I'm going to do 0.45 times the total number of females. How many do not have allergies? I'm going to do 0.55 times the total number of females. And so the values I get here are 10.35. Again, decimals are okay. Is greater than or equal to 5, so we're good there. And the value I get here is 12.65, which is greater than or equal to 5. And now I'm going to check for males. So I expect 45% of males to have allergies. So 45% of the 17 gives me a value of 7.65. That is greater than or equal to 5, so I'm good. And then I'm going to do the 55% of my males should not have allergies. So 0.55 times 17, which gives me 9.35. And those all look good for that large sample. So now I'm going to go to independent, and it's reasonable to assume that there's more than 400 students. And now we're going to go ahead and calculate our chi-squared. So for chi-squared, again, our actual value, 10 females have allergies, minus our expected value, 10.35, squared divided by the expected value of 10.35. Then I'm going to move on to females that don't have allergies, so 13 minus that expected value of 12.65, squared divided by 12.65. And again, we get the idea, so we're just going to put the plus dot dot dot, and we calculate that chi-squared, and we get, okay, 0.0506. It looks wrong, but I double checked my work. So we're good there. So now we're going to calculate that probability, so chi-squared CDF. Lower bound is 0.0506. Upper bound is really, really big. Our degrees of freedom, well, it's a two-way table, 2 by 2. So 1 times 1 gives us 1. And we calculate that probability, which is 0.822. We compare it to our significance level. Is it less than 0.05? Definitely not. So since our value is not less than 0.05, we fail to reject. Our null hypothesis, which means we do not have convincing evidence that there is a relationship between gender and allergies. Follow-up not needed because we failed to reject. Okay, big question that comes at the end, what test should we use? So, if you're looking for goodness of fit test is used when you have one variable and one population. There's usually a one-way table to analyze the distribution of one variable. Like favorite color. My one variable. I'm just going to measure the favorite color of everyone that I sample. Now, for homogeneity, we're going to have one variable, multiple populations. So now I'm going to ask all females what their favorite color is. I'm going to ask all males what their favorite color is. Or I'm going to ask all kids, or I'm going to take a sample of kids in Texas, what's your favorite color? And a sample of kids in Alaska, and what's your favorite color? And I'm going to look to see if there's differences between those groups. That's our homogeneity test. Now, for association, we're going to have two variables, one population. So I do a sample, and I'm measuring two things. So in every person in my sample, I'm going to ask, what state are you from? And what's your favorite color? So I'm measuring two things from everyone in my sample. Please remember that the difference between homogeneity and association is how the data is collected. Everything else is exactly the same. So let's go ahead and take a look at a problem and kind of talk about what test would be most appropriate. So an article in the Arizona Daily Star in April 9th of 2009 included the following table. We have these age groups and how many use online social networks and how many do not use online social networks. Suppose that you decide to analyze this data using a chi-squared test. However, without any additional information about how the data was collected, it isn't possible to know what chi-square test is appropriate. So the question A, how would you know that a goodness of fit test, so goodness of fit test is not appropriate? So how do we know it's not appropriate? Well, we're measuring two variables. We've got this variable here and this variable here. So that is really a two-way table, and for a goodness of fit test, we're measuring one variable. So we have two variables being measured. And the goodness of fit test has one variable being measured. Okay, describe how these data could have been collected so you could use a test for homogeneity. So a test for homogeneity would mean that one of my variables is going to be my explanatory variable. So does using a social network explain age, or does age maybe explain the use of social networks? Well, we would usually think that age would explain whether or not they use social networks. So we would want to make 6 random samples. Where each sample was an age group. And that makes the most sense. 6 random samples, each one was an age group. Because we would expect age to be an explanatory variable on the use of social networking. Now you can do it backwards. If you think that social networking would cause age, which doesn't seem to be explanatory, wouldn't explain an age. Seems kind of backwards. Then you could do 2 random samples of online social networking, no online social networking, and then measure age. But again, it doesn't really make sense when you think about explanatory versus response variable. Okay, describe how these data could be collected so a test for association or independence is appropriate. So this time we're going to do 1 random sample. But we're going to ask 2 questions. We're going to ask age, and then we're going to ask about social networking. And for this situation, the test for association and independence just seems to make the most sense. Because you can kind of look at a person and kind of tell age, but really the best way to truly random sample that is just you're sampling people and then you're going to ask about age and social networking. Where if you have something like gender, it's a little bit easier, not always. But if you have something like where people live, like Texas and Alaska, then it's easier to do 2 different samples and look for a test of homogeneity. So again, depending on what you're actually looking for, one will be more appropriate than the other.